Good morning, class. Let's look at solving a couple of simple first order systems, an RC circuit and an RL circuit. So let's take this example problem first. We have a power supply, a resistor. Now we have a switch which opens up at time equals 0, a 4K ohm resistor in parallel with a 3 millifarad capacitor. And we're given the information that the switch has been closed a long time. The switch opens at time equals 0, and we want to find a function V out, the voltage across it, which is also the voltage across the capacitor for time greater than 0. So we're pretty sure that we're going to be looking at the natural response, so we want to end up with a solution that looks like, now that's a V, believe it or not. Lowercase v is for a time varying voltage, uppercase V is for a constant voltage. All right, so we have V out. It's going to look like this. We need our voltage across the capacitor at time 0, and then we're going to have a decaying exponential minus t over tau. So there's two unknowns in this formula. We need to know the voltage across the capacitor at time 0, and we need to figure out what tau is going to be. So a key feature here is this switch which opens at time 0. That means we have one circuit before the switch opens at time less than 0, and we have a completely different circuit after time 0. So before the switch opens, what do we have going on before the switch opens? Now, we're given the information that the switch has been closed a long time. That's important. So that means our capacitor is in steady state. And you all know that at steady state, I'm going to be lazy and abbreviate. At steady state, it's been closed a long time, the capacitor is all charged up, and a capacitor acts like an open. Capacitor acts like an open. So, what does our circuit look like for this situation? Before the switch opens, we have a circuit that looks like this. We have the 2K ohm. There's our switch that's closed before time of 0. There's my 4K ohm capacitor, or excuse me, resistor. Now here's my capacitor over here, and it's acts like an open, so I'm just going to draw it like this. So before the switch opens, this is what we have. And there's my voltage at 0 minus. This is just 0 minus, just before the switch opens. And I can see no current at all is going to go through this open circuit. So we have a simple voltage divider. So my voltage at 0 minus is just a voltage divider equation. 6 and 2 and the 4. We have 6 volts times 4K over 2K plus 4K. So my voltage at 0 minus is equal to 4 volts. And remember that the voltage across a capacitor cannot change instantaneously. So just before the switch closes, it's 4 volts. That means that just after the switch closes or opens, it's also 4 volts. There we go. So we know right when the switch opens, it's 4 volts. So we now know this term, the voltage at time 0. That's 4 volts right there. Okay, now all we need to do is find tau. Okay, so for t greater than 0. Now the switch opens, which disconnects this resistor and the power supply. It's all disconnected now, and the only thing we have is the capacitor, which is now charged up to 4 volts, and this resistor. The time greater than 0, what does our circuit look like? We have, well, there's our switch. There's a circuit which is no current is going through. Here's our 4K ohms. And it's connected to my capacitor, which is 3 millifarads. And there's my voltage out. Okay, so we are in luck. Yes, it is a source-free RC circuit. This is important. We need to pay attention to that because this equation, which is one we're trying to solve, only works for source-free RC circuits. And that's what we have at this point. Let's see. We now have we need tau. So for a source-free RC circuit, tau is R times C. So what do we have? That comes out to be R is 4K ohms, 4 times 10 to the third. Our capacitor is 3 milli, 3 times 10 to the minus third. So my tau in this case is 12 seconds. We're on the road to success. We know V sub 0. We know tau. So our voltage out, excuse me, as a function of time is V sub 0, 4 volts, e to the minus t over tau, 12. And that's in volts. Ta-da, there's our answer. Okay. All right, a simple RC circuit. Let's look at a RL circuit. Here we have a sample. We have a couple of resistors. We have an inductor. We have a power supply and a switch that opens at time 0. Notice that once the switch is opened, we'll just have inductor and resistors. So we're assuming it is going to be source free after it opens. So our current should be of the form I sub 0 e to the minus t over tau. And this comes right out of chapter 7 in your book, so you can read the derivation. I'm not going to give you that now. You're welcome. So let's see. First of all, we need to figure out how much current is going through this guy at time equals 0. Well, once again, we have two circuits. Before time equals 0, when the switch is closed, and after when it is open. So let's look at for time less than 0, when the switch is closed, and it's been closed a long time. So we need to remember, how does an inductor behave at steady state? An inductor at steady state, an inductor acts like a short. Short circuit. So before the switch opens, what do we have? Let's redraw the circuit. always redraw the circuit. You may think you can do it in your head, but better safe than sorry. All right, so there's my switch that's closed. I have a 3 ohm resistor here. I have R2, which is of unknown value. That's one of the things we need to figure out. And it's at steady state. It's been closed a long time, so the inductor can be replaced with a short circuit. All right, and the current through this is going to be the current just before the switch closes, which is also the current just after the switch closes, or in our equation, just I sub 0. Remember that for a capacitor, the current cannot change instantaneously. So for the instant before and the instant after, it's all going to be the same. So we just need to figure out how much current's going through here. Well, let's see. It may look like we have a current divider here, but notice we have 0 resistance in this leg, and we're going to have some resistance over here. We don't know what it is, but we're going to have some. So all of the current is going to go through the 0 resistance side. And this I sub 0 then, there's a bump there. All right. It's just going to be Ohm's law, voltage divided by the resistance, 12 volts, we're 3 ohms. That's going to give me 4 amps. So good, we're on the road. We've got this part of the equation. Now, tau, what about tau? We're given tau, it's 0.5 milliseconds, but what we don't know is R2. So we're going to need to find the value of this resistance. Okay. This is what the circuit looked like before the switch opens. After the switch opens, what do we have? Well, once this switch opens, no current is going to flow through this part of the circuit. Actually, no current is going to flow through the 3 ohm resistor because it's attached to an open. So the only current of interest to us is over here. We have this resistor and that inductor. So after the switch opens, we have R2 and this 2 millihenry inductor. That's a 2. There's my current. And this is attached to a resistor, but really who cares? No current's flowing over there, no current's flowing over there. So we just have these guys right here. Ah, yes, it is a source-free RL circuit, which is good. This formula only works for source-free circuits. We know that tau, we're given the information that tau is 0.5 milliseconds. So, and we know from this equation that tau is equal to L over R2. We want to solve for R2, doing a tiny little bit of algebra. R2 is L over tau. L is 2 millihenries. Tau is 0.5 milliseconds, so that gives me an R2 of, let's see, 4 ohms. So there's one of our unknowns. All right, so good. Now we know our current through the inductor is going to be 4 amps. 4 amps. E to the minus t over tau. And tau in this case is going to be 0.5 milliseconds. Now another way, they don't always want to write it like this. So you remember this is t over 0.0005. It could be rewritten as 4 e to the minus, let's see, what's 1 over 0.000? It would be minus 2,000. So these two are equivalent. Whoops, wait a minute, I forgot a 0. 2000 T. There we go. Those are equivalent, don't let them confuse you.